What if one of the most distant planets in our solar system started behaving in a way that nobody can explain? Not a theory, not a simulation, not a prediction from any existing model. Neptune, the cold, dark, forgotten giant at the edge of everything, is changing, its temperatures swinging wildly, its storms doing things they shouldn't, and the scientists watching it are choosing their words very, very carefully. So the question is, what is actually going on out there? To understand why what's happening right now is so strange, you first need to understand what Neptune actually is, and how remarkable it even is that we know it exists at all, because Neptune was not discovered by looking at the sky. It was discovered by looking at a piece of paper, and in the 1840s, astronomers noticed that Uranus, the planet just inside it, wasn't moving quite right. Its orbit had tiny irregularities, wobbles. Something was pulling on it from farther out. And a French mathematician named Urbain Le Verrier did the math, pointed to a spot in the sky, told astronomers to look there, and when they did in 1846, Neptune was exactly where he said it would be. One of the greatest predictions in the history of science. But after that initial discovery, Neptune essentially became an afterthought, taking 165 years to complete a single orbit, sitting nearly 4.5 billion kilometers away. And before the Voyager 2 spacecraft flew past it in 1989, we had almost no close-up data about it whatsoever. We knew it existed, we knew it was blue, and that was about it. But Voyager 2 changed everything, because in a matter of days, that one flyby gave us more information about Neptune than the previous 143 years of observation combined. We saw storms, we saw moons in extraordinary detail, we saw a planet somehow radiating nearly 3 times more heat than it receives from the sun. Neptune was already strange, but what we're seeing now is something else entirely. When Voyager 2 swept past Neptune in August of 1989, it captured something spectacular, a massive storm system in the southern hemisphere called the Great Dark Spot, roughly the size of Earth, swirling counterclockwise, violent and vast, and scientists compared it to Jupiter's Great Red Spot, assuming it would be a permanent defining feature of the planet for centuries. But 5 years later, Hubble looked at Neptune again, and the Great Dark Spot was completely gone, vanished, replaced by a new dark spot in the northern hemisphere, proving Neptune's storms weren't permanent fixtures at all, but born, raged, and died in timescales that shocked everyone. Through the 2000s and 2010s, astronomers began monitoring Neptune's temperature more carefully using ground-based infrared telescopes, and what they found was puzzling. Between 2003 and 2018, Neptune's southern stratosphere was steadily warming, not by a little, but by about 11 degrees Celsius in less than 2 decades. Extraordinary on a planet that receives almost no sunlight. Then, in a paper published in 2022 by a team led by astronomer Michael Roman at the University of Leicester, something even stranger emerged. After analyzing decades of thermal data, the team found that Neptune had cooled dramatically between 2003 and 2018, and then unexpectedly its south pole had surged in temperature by 11 degrees Celsius in just the final 2 years of their dataset, from 2018 to 2020, a feature with no clear precedent. No model had predicted it, no existing theory fully explained it, and right now in 2024 and 2025 scientists using the James Webb Space Telescope are continuing to monitor these changes with the sharpest instruments humanity has ever pointed at the outer solar system, and what they are finding continues to raise more questions than answers. Neptune's atmosphere is divided into layers much like Earth's, with the troposphere being the lower, denser layer where most weather happens, and above it the stratosphere, where scientists have been measuring these mysterious temperature swings. And while Neptune's axial tilt of about 28 degrees is similar to Earth's, its year lasts 165% of our years, meaning one Neptunian season lasts roughly 40 Earth years, and Neptune's southern hemisphere entered summer around 2005, so you'd expect gradual warming over the following decades. But the cooling that occurred simultaneously and the sudden polar heat spike don't match any clean seasonal model. One hypothesis is that changes in ultraviolet radiation from the sun, which fluctuates on an 11-year solar cycle, are affecting Neptune's stratosphere in ways still poorly understood. Think of it like this. If the sun subtly changes the chemistry of Neptune's upper atmosphere, It could affect how heat is absorbed and retained even from billions of kilometers away. And another hypothesis involves Neptune's internal heat engine, because unlike Uranus, which barely radiates internal heat at all, Neptune is actively pumping heat from its interior outward, the source of which remains a mystery, possibly gravitational compression or residual heat from the planet's formation 4-5 billion years ago, or something more exotic involving the behavior of water, ammonia, and methane under unimaginable pressure deep inside. And the honest answer is that both mechanisms are probably at play, and we don't yet know their proportions. For a long time, Neptune was treated as a kind of simplified system, a cold, stable, distant planet, interesting mostly as an artifact of the solar system's formation, with the assumption that its atmosphere, while dynamic, would behave in broadly predictable ways, that seasonal changes would be slow and gradual, that storms would follow recognizable patterns, and that the planet being so far from the sun would be relatively insulated from solar variability. None of those assumptions have cleanly held up. The disappearance of the Great Dark Spot in the 1990s was the first serious shock. The thermal swings of the 2000s and 2020s were another, and each time the response from the scientific community has been the same. Go back to the models, revise the assumptions, collect more data. And what's been especially humbling is the realization that our observation record for Neptune is incredibly short, because 1989 was effectively our first real look, and in cosmic timescales we've been watching this planet for the blink of an eye. Imagine trying to understand Earth's climate if you'd only been watching it for 35 years. You might catch a drought, you might catch an El Niño, but you'd have almost no context for what normal even looked like, and that's exactly where we are with Neptune. So what is actually happening with Neptune right now? The most accurate answer is this. Neptune is undergoing atmospheric changes that are real, measurable, and faster than expected. And we don't fully understand why. The temperature swings are not an instrument error. They have been confirmed across multiple telescopes, multiple teams in multiple decades, and the south polar warming of 11 degrees Celsius between 2018 and 2020 is one of the most dramatic short-term planetary temperature changes ever recorded in the outer solar system, with the leading explanations involving some combination of seasonal solar effects driven by Neptune's long orbital cycle, solar activity modulating ultraviolet radiation and stratospheric chemistry, and Neptune's mysterious internal heat source behaving in ways that don't neatly correlate with external factors. And what makes this genuinely important beyond being a fascinating anomaly is what it tells us about planetary atmospheres in general, because we are now discovering thousands of planets around other stars, many of them ice giants similar in composition to Neptune, and if Neptune's atmosphere can swing this dramatically, and this unpredictably, it forces us to revise how we model all such worlds, with the James Webb Space Telescope now capturing data about Neptune's atmosphere with a clarity that was literally impossible 5 years ago. There's something quietly profound about Neptune. It exists at a distance so vast that sunlight takes over 4 hours to reach it. A radio signal traveling at the speed of light takes more than 4 hours to get back to Earth. It is in almost every practical sense unreachably far away, and yet it is changing right now, in ways that challenge our models, revise our assumptions, and remind us that even in a solar system we've studied for centuries, there are still deep mysteries sitting right in our own backyard, and we tend to look outward for the unknown, to distant galaxies, to the edge of the observable universe, to the question of life beyond Earth. But sometimes the unknown is closer than that. Sometimes it's a cold blue swirling world 4.5 billion kilometers away, doing something that nobody predicted for reasons we haven't fully worked out yet, and that perhaps is the most honest thing science can say. We're still figuring it out, and that's not a failure, that's the whole point.